All right, this next piece is about zeros of multiplicity. This is section C of section 3.4, starting on page 334. Let me go like this. We're going to go to this view. So page 334. I want you to note with me first this red and this green line down here. And their equations are over here. This green line is the equation, y equals x minus 3. You can see because it's a linear equation, its y-intercept is -3, but also its x-intercept is +3. Plug in a 0 there, or 3 there, you get 0 for y. And so it goes through this point. This red equation here also goes through that point. This red equation is y equals, or f of x equals negative, or x minus 3 cubed. The only difference between this green line and this red line is this red exponent. This one, x minus 3, has a root, or a factor, x minus 3, and a root at 3. This one has a factors x minus 3 and a root at 3. So they both cross through the x-axis at the same spot. But notice the difference. This one goes straight through. Goes straight through. Why? Because the multiplicity is 1. This one kind of flattens out there and then goes through. Why? Because its multiplicity is higher. And in fact, if I showed you y equals x to the fifth, you would see something that is even a little more flat. Let me grab black for a second. You'd see something that looks kind of like this. It'd just be a little wider and a little more flat before going up and through. Okay? And it'd be even steeper. So that would be y equals x minus 3 to the fifth power. What I'm saying here is as the multiplicity increases, the graph flattens out more and more around the root. Okay? So there you see that. Now look over here in the blue. We have y equals x squared. That should be familiar. Or not y equals x squared, sorry, because it's not centered at the origin. It's actually y equals x plus 2 squared. So it has a root at -2, and it bounces off at that point because the multiplicity is 2. Notice the purple one also bounces off at -2, but is a little broader. Why? Because its multiplicity is higher, so it flattens out more at that point. Let's go to the next slide. Naming attributes of a function from its graph, and here's the graph. It says the graph of the function f of x is shown. State whether the degree of the function is even or odd. Use the graph to name the zeros of the function, then state whether their multiplicity is even or odd. State the minimum possible degree of f, and state the domain and range. Well, let's look at the end behavior first. End behavior is down, up. Therefore, we know it has to be odd. So the answer there is odd. Use the graph to name the zeros. Well, there's a 0 there, and because it flattens out and doesn't go straight through, I know the multiplicity there is at least 3. M is greater than or equal to 3. Right here, it bounces off, so I know M is greater than or equal to 2. But here it's definitely odd because it goes through, and there it's definitely even. And then, let's see, there are 1, 2, 3. Let's count the multiplicities. That's at least 3 plus at least 2 makes it at least 5, right? The roots and zeros are at -3 and 2. -3 has a multiplicity of at least 3. 2 has a multiplicity of at least 2. So the degree is going to be at least 5. Now, when you count the bends, there's 1, 2, 3, so you know the multiplicity is at least 4. But because it's down up, you know that it can't be even, so it's got to be at least 5. So I actually wrote this as a possible polynomial to describe this. If you look at it and you actually cube 3, you get 27, right? 27. And you cube -2, you get 4. 27 times 4 is 108. So if this were the actual function, it would go through at 108. You can see here it goes through at like 11. So what does that mean? Maybe there's a multiplier in front, but these are indeed the correct roots, possibly the correct multiplicities. This might not be 3, it could be 5. This could be 4, you know, it just depends how flat it is at those points. What I did, let me pause. What I did here is because I knew that it had a root at -3. If it has a root at -3, then it has a factor x plus 3, right? If it has a root at +2, then it has a factor x minus 2. And I put in the multiplicities. Now, check out the next page. When I graph this using my graphing software, you can see the red line was the graph of this thing. And it went crazy, off the hook, shot out. Why? Because we know that the crossing spot for that is 108. The y-intercept of that is 108. Obviously not 11. So I put a little 0.1 in front. Now look how close this comes to the graph on the previous page. Look at my blue graph. Look at their blue graph. Pretty close, right? It's not exact. It might be that this multiplicity is wider because theirs looks a little more flat, but you know, we have a good idea. Finally, it says state the domain and range of f. Since it's an odd function, or it has an odd degree. Well, first of all, polynomials are defined. Polynomials are defined for all real x's. Okay, so the domain is x belongs to -infinity to +infinity. Why is that? Because you can plug in any value of x into this function and you'll get an answer. The range, however, you got to watch out if the function is even. In this case, the function's odd, so you can see if I draw a horizontal line anywhere, it will hit the graph somewhere, and that y will map back to an x. However, when you're doing an even function, you got to watch out in case there's a low point, because say this low point here is at -4, then the domain of that function would be y's greater than or equal to 4, or y's belonging to the interval, -4, -4 to +infinity, bracket there, parenthesis there. All right, let me stop this recording and we'll do the next example.